All right, today we're going to take a look at section 10.2, which is plane curves and parametric equations. And to kind of give you a little bit of a setup for why we would want to do this, we're going to start with thinking about a particular type of an example. So we often find it convenient to describe a location in terms of the parameter time. So to give you an idea of that, consider a batter hitting a ball. Its location, that is the ball's location, depends on the length of time since it was hit. As I'm even writing this down, I actually thought of maybe a better example would be like a pinball machine. Do you guys know what a pinball machine looks like? Okay, I haven't dated myself too much. They still have those things? Okay, fantastic. I haven't seen one in a long time. So the only problem with my example here is that there is a three-dimensional effect to it, right? You hit the baseball. You've got an X distance and a Y distance, from the two sidelines, and you've also got a height, how far it is off of the ground. A pinball machine would not have that height distance talking about it, so that may be a better example of what we're talking about. But if we could isolate looking down on top of the baseball field, right, and only consider the X and the Y as the two sidelines for first and third base, then we could still talk about it in this sense. Okay, so talking about where the ball is directly related to how long it's been since it was hit. Does that make sense to everyone? Okay. So, yeah, I'll write that down just so that you have it. Thus, we could talk about its two-dimensional location with X and Y in terms of time t. That is, X is actually an equation that is dependent upon t, and Y is another equation that also depends upon t. These are called, or are, parametric equations. I'm not going to have enough space on this slide, so when everyone's done, I'll do the example in the next one. Everybody good for me to switch? Not quite. Good now? Okay. All right, so here's an example. Our directions are to sketch the curve defined by the given parametric equation and write the corresponding rectangular equation. That's what we are used to using. It's called a rectangular equation. By eliminating the parameter. And our parametric equations are x equals 1 plus 2 cosine t, and y equals negative 2 plus 2 sine t. All right, so in order to do this in terms of drawing the curve, we're going to use the calculator here in a little bit. I'm going to show you how to use parametric equations mode in your calculator. But before we get to that point, what I want to show you is how you would do it sort of like old school. Like if you were first graphing equations, like in my algebra class, they did this about a week ago. We plotted points to graph equations. So instead of talking about the fact that an x squared curve looks like a parabola and so forth, we just plotted 5 points and we connected them and we got a basic shape of a parabola, okay? We're going to do that same sort of thing here. And just like with them and back in the day when you guys did it, there are no specifically good directions on how you choose your points. It kind of depends on the types of equations you're looking at. So for example, these are trig functions, right? So plugging in t equal 1 and finding out what is the sine of 1 and the cosine of 1 is not especially friendly. Agreed? But there are trig values, like, you know, radian values, right, that are much nicer to work with for trig functions. For example, we'll start with 0 just because 0 is typically speaking a nice value to work with for anything. And if you need some little scratch work over to the side, and I'll do a little bit as we go too, we have this to be 1 plus 2 cosine of 0. So do you guys remember what cosine of 0 is? It's 1. So this is actually 1 times 2, and then plus 1 to give me a 3. So my x value is 3. And then we're going to do the same thing with y. We've got negative 2 plus 2 sine 0. Does anybody remember what sine 0 is? That's 0. So this ends up giving me just a negative 2. Okay, so far so good? Okay, so those are values of 0. And because this is trig values, like I said, we don't want to use, say, 1 next. If we were doing some of the other equations that didn't have trig involved, 1 might be a very good choice to do next. And then 2, and then 3, right? Those could be really valuable places to check. Not so pretty here. But pi over 2 would be really nice, wouldn't it? Because sine and cosine alternate between being 1 and negative 1 and 0 at the pi over 2 values. So let's use that to our advantage. So let's try pi over 2. So if I go back up to my equations up here, and I put in a pi over 2, so I've got the cosine of pi over 2. What's the cosine of pi over 2? That's 0. So I get 1 plus 0, so that would be 1. And what if I did the sine of pi over 2? That's 1. And then I have 2 times 1 would be 2, plus the negative 2 at the beginning would be 0. So I get a 0 on that one. What would I try after pi over 2 if I'm on this sort of a pattern? Pi, what did you say, Ethan?
3 and negative 2.
Oh, you're saying what the values would be. Okay, so let's double check. You're really close. So what happens if I use pi instead of pi over 2? So I've got a pi here. So when I do cosine of pi, I get -1 times my 2 would be -2 plus my 1 would be -1. Eventually it'll cycle back onto itself though. What about sine of pi? That's 0. So this actually gives me the point -2 again. So the y value stayed the same, the x value was different. What would I try after pi? 3 pi over 2. What's that? Yeah, we're going to do one more after that just to show that it cycles back to itself. Yeah. So if I put 3 pi over 2, what is the cosine of 3 pi over 2? That's 0, right? And then I've just got the 1 at the beginning. And what if I do sine of 3 pi over 2? -1. So now I have -2 plus a -2 would be, it would be -4. And then just for, kicks and giggles, like I just told Kyle, we're going to try it for 2 pi. And what's going to happen when I put 2 pi in? Yeah, I'm going to get right back to where I began, right? At 3, -2. All right, plot these on a graph, okay? Put all those 4 points. It's really 4 because they start duplicating. Plot them on a graph and see what kind of a sketch you end up getting. Ooh, if you connect them that way, you could. Do you think that's what's really going to happen since they were trig functions that... Yeah, it's actually going to be a circle. So let me plot mine. What do I have? 3, -2, 1, 0, -1, -2, 1, -4. And if I plotted them with straight edges, like Ethan had seen, right? Like connect the dots like a child at the Chili's, right? It does look like a diamond. No, I'm saying like that's what I would have thought to do too if I was connecting the dots. That's exactly what it looks like. But when we go back and we consider the sine and the cosine values, and if you aren't sure, like do I connect them that way? You could always try something between them, right? What would be a value that we could try between 0 and pi over 2? Pi over 4 would be a good choice, right? And it would give us a good idea of how the curve actually looks. But whoever sort of supposed what it might look like as a circle was actually correct. It does look like a circle. I don't know that I got it very good there. Let me move mine over. No, I didn't. You could tolerate it? But what if I can't?
I think you got a lot more circles around these areas.
All right. All right, I think I can tolerate that one. That one's pretty good. It's not bad. Okay, there's one more thing that we need to do on this diagram that we haven't done. This happens because it's parametric equations, okay? So we're going to put the direction that the curve is moving, right? Which one did you plot first on this picture? Over here, right? And then we went up like this and around. So we're going to draw arrows indicating the direction of the curvature, like this. Now, this is a very nice one. It's a circle. It just repeats itself, right? It continues to repeat itself. Not all curves do that. I'm going to show you one here in a minute what you're going to do with your calculator that doesn't have that feature. We haven't done one of the bits of direction, though. It also tells us that we're supposed to write the corresponding rectangular equation. Now, we know this is a circle. So the nuts and bolts are that if you've gotten to this point, you probably can give me the equation of this circle without doing what I'm about to show you to do. But that actually requires that you know the shape that you're dealing with, and sometimes it's harder to see than just a circle. So let me walk you through how you would go about eliminating the perimeter in a situation where you might not know what exactly it looks like when you're done. Okay, so we're going to take the equations that were given, and typically speaking, let me write this as a note. To change to to a rectangular equation, we will often use substitution. i.e., solve one of the equations, I'm just going to say x of t, in terms of t equals something, then substitute that value for t into y of t. That's typically what we're going to do. But do you see that here that would not be especially friendly? If I wanted to solve for t in these equations, I'm going to have to do a little subtraction, but then I'm going to have to use arc sine and arc cosine, or the inverse sine and the inverse cosine, and that's not especially pretty. So it's not a very good idea if we're dealing with trig functions, okay? If we're dealing with other functions, it works really well. But for trig functions, there's something else we're going to try. So this won't work well. This method won't work well for trig functions. It's a bummer. So what are we going to do? Well, I'm going to show you, and this is why I chose this one, is I wanted to show you one of the tricks of the trade, if you will. Okay? And so this is one of those. So let me write down for you the equations we had to begin with on the second screen here. X is equal to 1 plus 2 cosine of t, and y is equal to negative 2 plus 2 sine of t. And you actually have at your disposal, we're going to use this here in a minute, a very cool fact that you know from trig, that sine squared of theta plus the cosine squared of theta is equal to what? 1. And it's called a Pythagorean identity. And it's not the only Pythagorean identity. There's also one for secant and tangent, and there's one for cosecant and cotangent. And you may need to access those as you're looking at these as well, okay? So those three Pythagorean identities, what they're called, are quite useful. So, you know, that's all well and good, but if I were to square sine and square cosine from where they are right now, I'd have to square the whole side of the equation, and it's got addition and subtraction on it on the right-hand side, right? So I don't really want to do that. So what we're going to do is we're going to rewrite each of these equations slightly. So I've got x minus 1, and that equals 2 cosine of t. And I've got y plus 2, which is equal to 2 sine of t. Everybody good so far? Okay. Super much friendlier to square this on the sides of the equation than it was the previous ones, because the squaring will isolate only the trig function. I know I've got the 2 in front of it. That actually works out really nicely. But that's not the problem. It's the addition and subtraction that's the problem. So if I were to square both sides of these, and I were to add them together, right? Old-fashioned addition like back in, second grade, like that. I could actually rewrite this as x minus 1 squared plus y plus 2 squared, which should look like a circle, right? Yeah. And then this would equal 4 cosine squared of t plus 4 sine squared of t. Does that look right? What does the right-hand side equal? 4. And if you aren't sure looking at that, if you couldn't have answered that right away, think about factoring that 4 out. And here's the cosine squared plus the sine squared. that we identified just a moment ago as equaling 1, right? So all of this is the same. I'm not going to rewrite it in that step. But this will end up equaling 4. So my rectangular equation is actually x minus 1 squared plus y plus 2 squared equals 4. Now let's go back to our graph and make sure that it actually is that equation. I mean, that's probably smart, right? We should be able to check ourselves and make sure that it actually works. So this equation would have a center where 1, negative 2, and it would have a radius of what? Of 2. Okay, so this center is the center at 1, negative 2. Sorry, my grid's gone, but hopefully yours might have been there. I believe it is. And does it have a radius of 2? Yeah, I think it did. So that would be the trick for how to deal with parameters that you can't always isolate very well. Okay? I think you're going to have a parameter to isolate that has exponents. Like it has one that looks something like e to the t, like this. How would I isolate that t? Logs, right? So I think you're going to get to do one like that as well. All right, very good. I would like for you to grab your calculators out if you have them with you, and we'll see if I can get this screen here to work for me. Let me write down my stuff on the board before I switch to that screen, though. So, for example, we're going to look at using our calculator. So use a graphing utility. To sketch the curve. Defined by and this is the one we're going to do. X equals t cubed minus 2t. Y equals t squared minus 3. I'm going to show you. That's what I'm going to do next. I just want to make sure you had it written down before I try to make this thing work. And we're going to hope that my calculator batteries don't die for us. So they're low. Okay, does everybody have that written down from the screen before I move to the other device? If it's input A or input B, let's give it a shot. That didn't do anything. That's it. Gotta remember. All right, that's pretty good. All right, hit mode. Maybe your mode screen doesn't look exactly like mine, but hopefully everyone sees an option down here that says PAR. Do you guys see that on your screen? Choose that one. PAR is for parametric. And if you hit Y equals, you now have an X and a Y equation that you get to enter into your calculator. Super cool stuff, right? Not only that, we'll turn my plot 1 off because I don't know what that's on there for, probably from calculus when I did that. But what you're going to do then is you're going to put each of these equations that we had on our screen. So not only are you going to have x of t, like the subscript t, but when I press the X button, what's it going to say? It actually says t, right? That actually says t, and so I've got t cubed minus 2t, and my y equation is t squared minus 3. Don't jump the gun and graph it yet. Just enter it for the moment. Did you say oops? Kyle. All right, did everybody get that entered? All right, I'd like for you to click on window. Now, a moment ago when we were graphing by hand, I mentioned the fact that there's not a set like t is always going to be, you know, these 5 values. I mean, it doesn't work like that. We chose the particular values we chose because they were very nice for using inside of trig functions, right? So if we had done what we just did and we did that on the calculator, then what mine is currently set up at would be pretty good. Right now, that's going from 0 to 2 pi. That's what my screen's set up as, right? For x, my t max and my t min. And this t step tells it how quickly it happens. So if you do it really, really slow, like you do a really, really small t value, it sketches the curve really, really slowly. If you do the t-step value to be really big, it sketches the graph really quickly. But you have to be careful. You might be like, well, I want it to do it as fast as possible. But if it does it too fast, it'll do what Ethan suggested it might have done, and it will connect points that it actually isn't supposed to connect. So you want it to graph somewhat slowly, because basically what it's doing is it's calculating every single iteration that you asked for and plotting a point that it's then going to connect together. So what we want to do right now, let's just start at t equals 0 and let's go to t equals 10. I have no idea if that's going to work. I didn't actually try this before I got here. Yeah, that's the way that went today. All right, and we'll make our t-step, we'll just adjust it. Let's just say t-step 1 for right now. Now the y-min, or the x-max, x-min scale, y-min, y-max scale, that's all the same thing you've seen before. And we don't necessarily have a real good idea of what to do, but our standard is -10 to 10, right? So let's just set it -10 to 10 and see what happens. We can always come back and adjust it if it's no good. And the scale, I always leave at 1 unless there's, you know, some reason to change it, and that would usually mean we're dealing with really large values. So if I graph it, it graphed really fast, and it looks very sharp. And most of the time we're dealing with these, they're not sharp graphs. These are curves, right? So it'd probably be a good idea to graph it a little bit slower than a t-step of 1. Also notice there's nothing on the left-hand side of this graph or on the bottom of the graph. So if I wanted to sort of zoom in on my location, it would not be a bad idea either. My x value going over here to 10 is not bad though. That looks like it's continuing in that direction. So I'm going to change my window a little bit. I'm going to make my t-step maybe 0.2. Okay, I'm just guessing, right? And I'm going to make my x minimum bigger. I don't need it quite as low, so maybe like -2, and my y minimum like -2. So it's no longer going to look centered. Ooh, that was not good. -2 was not a good one for the x. How about -4? I didn't mean x, I meant y. Oh my goodness. Let's try that again. -2 for x, -4 for y. That looks better. Okay, so right now my x minimum is -2 with an x max of 10. My y minimum is -4 with a y max of 10. My t-step was at a 0.2. And we end up with a curve that looks like what? This looks like a parabola, right? If my t value had started negative, which I could have, I would have had sort of the other portion half-ish of the parabola. So we will pause here today. We will draw this in next time and continue from there.
Homework still due though, right?
No. The homework is not going to be due on this on Wednesday. The homework from 10.1 will, okay?